So this is the day one video for section 7.2, the area of a region between two curves. We're still looking at this essential question, how do integrals explain physical quantities? We're going to kind of frame this around the St. Louis Arch here. And well, a lot of people think that the shape of the St. Louis Arch is a parabola. It's actually something called a catenary. And a catenary is the shape that a hanging rope or a hanging chain takes on under the force of gravity. And the neat thing from an engineering aspect about a catenary is that it directs its own weight down to the foundation without any shear. So in other words, the shear would be like a horizontal force in this structure, and this way, this type of structure, all the forces, all the horizontal forces, which would cause it to kind of peen out at the bottom, or kind of flatten out, they don't exist. Everything is directed vertically down to the foundation, so it's a very stable structure. And catenary is a little, it's not quite as pointy as a parabola is at the vertex. It's a little flatter and a little wider. So this is just a quick discussion here. It's not in your notes. But if we go back to our definition of a definite integral from the last unit, so if we have a function and we want to take the definite integral of that function from a to b, then this definition then really strictly says that we're capturing the value of this region, and the real strict wording is that it's the value of the region that's between the function and the horizontal axis, so between this function and this axis in this area from a to b. So it's the shaded area. That's the real strict definition of a definite integral, and we're going to use that definition to help us answer that essential question, and that is that we want to work on using that definition of a definite integral to represent physical quantities. So for instance, this blue region here, if we want to find the area of that, a physical quantity of that blue region would be its area. And so if we could then take a look at the real strict definition of a definite integral, go back to the definition of the definite integral for f of x, we know it's that value of that region between the function and the horizontal axis. And then if we look at the other function that was beneath it, g of x, we can use that definition as well, as the value of the definite integral is that region underneath the g of x curve between that and the horizontal axis. So if we superimpose those two curves, then we can take the value of the definite integral of f of x and subtract g of x and get this, a physical number that represents this blue region. And so we can use then that definition of the definite integral to find the area of that region. And if you notice, if we kind of go back to the previous picture, it's the green region, the integral of f of x, minus the red region, the integral of g of x. And since both those regions are above the y-axis, they're both positive in value. So when we subtract them, we get the remaining region. And so if we go then and kind of extend that to what happens when we have a curve below the axis, then the green region doesn't change. It's still the definite integral. It's still above the axis, still positive. This region is beneath the x-axis, so the value of this definite integral is going to be negative. So even if we subtract the two values, we'll have a positive value minus a negative value. Minus a negative is the same as adding, so we still get a positive value for the definite integral of that whole region if we still subtract them. So we've come up with a method that works no matter where this lower curve or one of these curves is located. So if it works for any situation, then we can extend that and say that that's the formula to find the area between two curves for any given situation. So we're going to use this then to calculate the area of some enclosed regions. The nice thing is this answer will always be positive, and that's advantageous because we are talking about area, and area is always a positive number. So this is how we're using the definition of definite integrals to lead to explaining a physical quantity, and that physical quantity is area. So if we take a look at the true definition out of the textbook, one thing that's helpful is to draw what we call representative rectangle. And that rectangle, if we can get an expression for its area, we know that if we go from A to B, we can just stack rectangles across that shape, and that's the act of integrating. So this rectangle then has an upper curve for its top and a lower curve for its bottom. So its height is going to be the upper curve minus the lower curve, or f of x minus g of x, and its width is going to be dx. So this expression right here, part of the integral expression, it represents the area of this single rectangle. And then the integration process is going to allow us to stack rectangles from A to B. And when we're doing that, we will find the area of the entire region. So, so that gives us kind of a general strategy then. First, we want to make sure we have a sketch for the curve and kind of have an idea of where that shaded area is. And then we're going to have to decide if we have horizontal or vertical rectangles. For this for this first section, we're going to talk strictly about vertical rectangles. The next piece of the next video, we'll talk about horizontal rectangles. We're going to write an expression for the area of that rectangle. And it's going to be a dx expression today, and tomorrow will be a dy expression, but we'll get more into that tomorrow. And then we'll find the limits of integration. So where do we want to start and stop this shape? And then we're going to go ahead and integrate and evaluate to find the area, the physical quantity. So, and you have those steps in your notes for that strategy. And I have it up here as a quick reference. So finding the area between these two curves. So let's go ahead and get a sketch. And there's that parabola in red, and then the line in blue. And we're looking from -1 to 2. So we're looking for that enclosed area. So if we take a look then and kind of shade in that area, we're looking at finding the physical quantity for the area of that region. So we want to set up a vertical rectangle here, and that vertical rectangle goes from the top curve to the bottom curve. So it's our f of g minus our f of x minus our g of x. And so we're going to go ahead then and set this up algebraically. So here's our sketch of the curve, and here's our shaded region. And then we're going to go ahead and get our in this case, our vertical rectangle drawn here with our dx, that's the width of our rectangle, and the height of our rectangle is going to be f of x minus g of x, or in reference to this setup and these variables, it's going to be y1 minus y2. So I'm going to go ahead and write the expression for the area. So the area is going to be, just going back to geometry, length times width. We'll consider this the length of the rectangle and the width of the rectangle. So the length then is going to be the parabola here minus the line. So that's our f of x minus our g of x, written in the terms of these variables, times our dx. So I'm going to keep getting this. I want to get this area in terms of x, so I'm going to go ahead and substitute these functions in. So we have 2x minus x squared minus a negative x times dx, and simplifying that a little bit, we get 2x minus x squared plus x times dx. So this represents that single rectangle. And now we need to find out the points of intersection that enclose these shapes between these two curves. And so we can pick that up right from the sketch here. So we know we have the point of intersection at x equals -1 and x equals 2. If we didn't have grid lines and we needed to find that out algebraically, we could set the two equations equal to each other. So if you want to do this, you can, but we really can visually see the lower and the upper bound just from the graph. But if we did have to set the equations equal to each other and solve, we can get each term to the right side, recognize this as a quadratic that's factorable, and then we can get the right endpoint and the left endpoint. So we know we need to integrate this. This represents one rectangle. Integrating it represents the entire shaded region. And we're going to use this as the limits of our integration because that's where our shape starts and stops. And so as we set this up then for integration and evaluation, we have then the integral from of this rectangle, 2 minus x squared plus x dx, from -1 to 2. And then we're going to go ahead and integrate that. So the antiderivative of 2 is 2x. The antiderivative of minus x squared is minus x cubed over 3. And then plus x squared over 2. And we're going to evaluate that between -1 and 2. So plugging in 2 gets us 4 minus 8 over 3 plus 4 over 2, which is 2. And then minus the lower bound is a -1, so it's -2. Minus a -1/3 is going to be plus a third. And then squaring -1 is going to give us a +1, so it's going to be plus 1/2. And then simplifying that, then we're going to think of this as 12 over 3. This is 8 over 3, and this is 6 over 3. So we've got 12 minus 8, which is 4, plus 6, which is, 12 minus 8, which is 4, plus 6, which is 10. So this first set of brackets is 10/3. And then the second set of brackets, we need 6 as a common denominator. So this is -12 over 6. It's 2 over 6 and 3 over 6. So -12 plus 2 is -10. -10 plus 3 is -7. So this is minus a -7/6. And 10/3 is 26. So this is going to be 27 over 6 for the area of that region. Notice that it's positive. Because of the definition of our definite integral, we can subtract the upper curve minus the lower curve in that integration process. For example 2, we want to again find the area of the region bounded between x squared and x cubed. And between 0 and 1, the blue line is x squared. X squared is bigger than x cubed. So we're looking for the area of this region here that's enclosed by these 2 points. And again, we can find those 2 points algebraically, but we also can find that just by visual inspection. And then again, since the blue curve is on top and the red curve is on the bottom, we can create a rectangle that touches both curves for that entire region, and that rectangle is going to be vertical. So it's going to be a dx problem. So as we get that sketch on our paper here, we're going to go ahead then and set up our vertical rectangle and find the area of that vertical rectangle. So that single rectangle has a length times a width. That length is f of x minus g of x, and the width is dx. And so substituting in our functions, that gives us x squared minus x cubed dx. And we're going to integrate that between these two bounds, 0 and 1. And again, we can visually see, since we have grid lines, that those are the limits of integration. But if we want to find them algebraically, we set the two functions equal to each other and factor out our functions to find those points of intersection. So I can factor out an x squared, then I have an x minus 1 in the brackets, so I have a repeated root at 0 and another root at 1. And so that's going to set up our integration, and these are going to be the limits of that integration. So as we integrate then our representative rectangle, or as we integrate the area of that rectangle from 0 to 1, the antiderivative of x squared is x cubed over 3. The antiderivative of x cubed is x to the 4th over 4. We're going to evaluate that between 0 and 1. And so plugging in 1, we've got 1/3 minus 1/4. And plugging in 0, we've got 0. The common denominator here is 12. So we're going to think of this as 4 over 12 minus 3 over 12, which is 1 over 12. So the area of this light green region from from 0 to 1 is 1/12. Question 3 here, there looks like there's a lot going on, and there is. This is a calculator question from a recent AP test, and it's a sure bet. This is something that you're gonna see on the AP test, and as of right now, we can do parts A and B. We cannot do part C yet, and we cannot do part D yet. We'll come back and do those 2 parts after we do section 3. But we're going to concentrate on A and B for right now. And when we talk about scoring things like this, we're scoring things for components of our setup. So we'll kind of go over the scoring as we go through this. So we've got a region, it's bounded by the graphs sine of x and x cubed minus 4x. And so looking at this picture here, if you don't know which one is which, since this is a calculator part, graph them both on your calculator, make sure you're in radian mode, and so that you know exactly which function is which. But remember that sine oscillates, so it's a pretty sure bet that this oscillating one is probably sine x. But it might be a tough call because a cubic also could potentially oscillate. So it says when it asks you find the area of R, in other words the shaded region, it implies that you show your setup. Remember, your setup is showing the integration and the integrand and the dx and the upper and lower limits. So we'll go over that as we set this up. So here's our representative rectangle. Its height is going to be this upper curve minus the lower curve, or f of x minus g of x. So setting up this area then, we're going to have limits that are going to be start here and stop here. And from this sketch, it's a pretty sure bet that we're starting at 0 and ending at 2. Okay, and then this area is going to be, this upper curve is sine of x, and this lower curve is x cubed minus 4x. So the area then is going to be sine x minus x cubed minus 4x. And then we have our dx, that's our width. And then we're going to go from 0 to 2. So looking at these components here, from a grading standpoint, this is a three-point question. And this is how the points are awarded. You're awarded 1 point for these limits here, making sure that they're both present and correct. So 0 and 2 both need to be there. So that's 1 point. Its second point is for the integral symbol and the dx. So those are our calculus notations basically. So that's point number 2. And then the third point is making sure that you have the correct functions in the correct spots and that you have correct brackets. So in other words, we need a set of brackets here so that they know that the pi and the x is part of the trig function. And we need a set of brackets here, potentially, so that we know that we're subtracting this whole function. So we need minus bracket x cubed minus 4x bracket, and then cap it all off with a set of brackets before the dx. The only other alternative is to distribute the minus sign. So we could potentially have sine pi x minus x cubed plus 4x. That would be an alternative correct answer. So that would get you 3 out of 3 points. Make sure you're in radian mode. And this is a calculator question, so we're going to do an f int here. We do not show this f int in our test booklet. We just show the this setup and then the equals and then the answer. So as you put this into your calculator from 0 to 2, you'll get an answer of 4. So the total points here might be as much as 4 points. 3 points for the setup, 1 point for the answer. For this next part, I think actually this is labeled B in your notes. That part, in fact, let me just adjust this and change that to B. And go back and play. Okay, so we're going to do an integration by hand here. And because although this is a calculator question, this integration should be expected to be done by hand. What makes this a calculator part is what happens in the other sections that we're not going to talk about until a little later in the chapter. So I just want to practice integrating this. The sine of x is our integration on the quick. We have a linear inner function here. So integrating this on the quick, the antiderivative of sine is minus cosine, and then we put the pi x there, and then we have to divide by the derivative. And the derivative of pi x is pi. So that's the integration on the quick. You can also do your steps for a u sub here if you want. You'll get the same answer. Okay, then it's minus the quantity. The antiderivative of x cubed is x to the 4th over 4. And the antiderivative, got a minus 4 here, the antiderivative of x is x squared over 2. So there's the antiderivative from 0 to 4, or excuse me, from 0 to 2. And being a calculator question, I'm not going to substitute in the 2 and the 0. We know that that answers 4. But I just wanted to go over the antiderivative because that's a reasonable one to be done without a calculator. And the integration on the quick is the key to make that a fast integration. So at this point, I know we're only halfway done with that problem. And we'll continue that problem in the next video. So at this point, you have enough to do the first day of homework. If you're looking to do a Blackboard proficiency quiz, wait till the next, after the next day. Wait until after day 2 to do that.